अभी हमारा इस पर्टिकुलर एक्सपेरिमेंट का एजेंडा ये है कि वी वांट टू एनालाइज द इलेक्ट्रो ऑप्टिक इफेक्ट विद रिस्पेक्ट टू द कर मटेरियल्स. सो होता क्या है कि जब there are certain substances or materials जिसमें when we propagate light or we provide some external electric field, तो उस particular substance का refractive index change होता है. What I'm trying to say is the refractive index of that material is dependent on the electric field. Now that electric field can either be of the light that is propagating, or it can be the electric field that we get by the external source. तो जो पहला केस है जिसमें लाइट की वजह से, लाइट के इंटेंसिटी की वजह से चेंज आता है रिफ्रैक्टिव इंडेक्स में, उसमें the intensity of light has to be very high, then only it will create some significant impact onto the refractive index of the material. However, जो दूसरा केस है जिसमें हम लोग एक एक्सटर्नल पोटेंशियल अप्लाई करते हैं अक्रॉस द लॉन्गिट्यूडनल डिस्टेंस ऑफ योर वेव गाइड, अगर उसमें जब हम लोग पोटेंशियल अप्लाई करते हैं तो देयर इज सम चेंज इनटू द रिफ्रैक्टिव इंडेक्स ऑफ द सब्सटेंस. और जब ये रिफ्रैक्टिव इंडेक्स में चेंज आता है तो उस रिफ्रैक्टिव इंडेक्स की वजह से डेफिनेटली जो प्रोपोगेटिंग लाइट है उसके फेज में चेंज आता है. तो हम लोग का आज का एजेंडा है कि हमें देखना है कि हम लोग के लाइट जो प्रोपोगेटिंग लाइट है उसमें कितना फेज चेंज आ रहा है व्हेन वी आर पासिंग इट थ्रू द कर्व मटेरियल. For right now, the Kerr material that we are taking is lithium niobate, which whose molecular formula is LiNbO3, and LiNbO3 shows Pockels effect, and Pockels effect it shows Pockels effect which states that the electric field is directly proportional to the the refractive index is directly proportional to electric field. There are two there are two significant effects that happen, two significant phenomena. एक होता है Pockels effect और एक होता है Kerr effect. Pockels effect में directly proportional होता है refractive index E के, and in Kerr effect refractive index is directly proportional to square of electric field. ठीक है, तो ये एक बेसिक बैकग्राउंड है थ्योरी का जो कि इस एक्सपेरिमेंट में we are using. So this is the COMSOL multiphysics. We will be using COMSOL multiphysics software for modeling of our design. So we will start with model wizard. इसमें we will go for 2D for right now. Now, since we have to do the optic analysis as well as we have to apply the potential, so we'll have to use two different physics. The first one is EWFT, and the second one is electrostatics. So we will continue with these two physics in this experiment. General studies we can use for electrostatics. We are concerned with the entire experiment has been divided into three phases. The first phase is to optimize the dimensions of the waveguide in which the light has to pass. The second step will be to optimize the distance between the waveguide and the electrodes that we are placing. And at the third step, we will see that how the phase is related with respect to the potential that we apply across the waveguides. So, in first step, we will define the parameters. So, what parameters we require, we will put it one by one. And since this experiment is an SoI based experiment, which means that it is a silicon on insulator. So for insulator, we will be using SiO2, silica glass, and to extract the refractive index of silica glass, we will have to use Selmayr equation. So here we can see this is the Selmayr equation. Selmayr equation is used to find the refractive index when any particular light of one wavelength, like what I'm saying is it any monochromatic light when passes through the medium through SiO2, then how the refractive index of SiO2 changes. This is given by the Selmayr equation. As we can see, there are certain constants, and these constants we will be using. So these are the coefficients that we will use. Now we can define one more variable of voltage that we will use for giving the voltage supply across the waveguide. Now after this we can define the parameters, the variables for defining the geometry. For geometry, there will be width, there will be height, and there will be the length, or we can say the depth of the waveguide, as well as the electrodes. So for height of electrode, we gave it 200 nanometers, which is a standard value of fabrication. This is the standard height of the fabrication that we often very use. Width of the electrode. Now this parameter we have to optimize with respect to the confinement and the modal effective area. These will be the factors on which we will decide that what is the optimized value of width electrode. So for now we will just keep it 400 nanometers. This is a random value. As we know that in later in this meeting we will know that what is going to be the optimized value of it. And length of electrode HV and we can for now put it as 3 micrometer, which later again will be optimized in further sessions. So these three are the dimensions of the waveguide. Now, after defining the dimensions of the waveguide, we can define the parameters for the dimensions of the electrode. So, for the sake of symmetricity and uniformity, like a uniform structure, we will keep the length, width, as well as height of the electrode same as that of waveguide. So, as per now, there is no need to define other parameters for the dimensions of the electrode. Right now, the next thing is we can define the refractive indices of the different structures that we are going to use. So the first one is NSiO2, and for this we will use this equation which I have used in my previous experiment. So I'll just copy it from here, which is again the Selmayr equation that I shown previously. I will just copy it here. I hope there is some error. Let's see what error we are getting. Okay, so here it says that you have not defined a parameter called lambda, which I'm using in this equation. So I will define one more variable, which is lambda. Let's say we use 1550 nanometers for now. So once I define this, we will make this move down, and now I think it should not give error. B1 lam square B2 plus B3 B4. Okay, it is giving error because I have not defined B6. So we will copy it from here. This B6. Here we have defined all the parameters that were required for the refractive index of silica glass following the Selvar equation. Now, after that, we have to define. Now we have to define the refractive index of lithium niobate, which I will call it by NLI. NLI. Now here I will only mention the refractive index without the impact of the electric field, which is 2.29 for lithium niobate. And while defining the materials, I will include the relation of the electric field into the refractive index. Now let me analyze if I have written all the parameters that I have to include. So for now it looks good. After this, let's start defining the geometry. So geometry should be something like this. Now since we have to do the modal analysis for now, as we are doing the optimization, we will consider the cross-sectional view of the geometry of the waveguide and the electrode. So for that, we will define a rectangle, which we let's say waveguide. It will remain solid. We don't need V1. What would be the width? So width will be a wave. I have not defined it. Let's see what I have defined it. Yes. So here it will be a wave, and this here it will be edge of position will be from origin only, because we want to keep it symmetric, and base is going to be center, and everything is looking good. So here we will build it. So here we get the rectangular waveguide that in which we will be injecting the light and will be analyzing. After that, the next thing we have to define the silicon insulator on which we are mounting the waveguide. So for that, let's let, let's call it silicon insulator. It will again remain solid. For silicon insulator, we can what dimensions can we take? It depends on us. So we can take it like 4 into h with a wave and height of with a wave. Let's see what I've taken here. Then accordingly, we can take it. Although it really doesn't matter. Yeah, width of box. I have already defined other parameters. Define a parameter. Width of box, and let's say we can put any random value to width of box. Let's say just try with 1 micrometer. Then it becomes width of box. And similarly, we can define H box. Let's say 800 nanometers. And change the values as per our convenience. Here we are using H box of 200 nanometers because the height should be 200 nanometers. Accordingly, we will make the geometry. And similarly, we define an outside boundary. Okay, so now we have to move down the silicon insulator because we want such geometry. So, okay. So here our geometry is ready almost. So if I summarize that what I did in this geometry, so this domain this domain is the silicon dioxide, silicon SiO2 silica class, and this is the background. It can be embedded into it. So this is the cross section of the waveguide of the entire system of SOI, on which we will uh, fabricate the on which the fabrication of the waveguide will be done. And this particular area, this small rectangular domain, it is the wave spin that will be doped by lithium niobate. Okay. After this, we will define the materials. So for that, we will add materials from library. We will add lithium niobate. For that, I will search lithium niobate. There are two options. You can use this one. So this is lithium niobate. One more substance I have to search, it's silica glass. Now I have two substances, two materials that I have imported. Lithium niobate. As you will go down, first I will choose the domain. So it's not lithium niobate. Only this air domain is lithium niobate. Yeah, in this section, refractive index, I will define the refractive index of lithium niobate, which is NLI minus 0.5 into. Okay, now here I have to define one more parameter, which is the Pockle coefficient, or you can call Kerr coefficient. It really doesn't matter. I will call it by alpha, and alpha for this is 30.9 picometer per volt. So I will define it picometer per volt. I will use it in this definition of refractive index. Then I will delete it. NLI minus 0.5 into alpha into NLI sorry NLI cube into PS dot non T. I think it's correct. Let me check. Let me see. NLI, and here NLI is the refractive index of lithium niobate when there is no impact of electric field. So NLI minus 0.5 into Pockle constant into cube of NLI into the electric field. Now here ES dot norm E is the electric field when the potential will be applied across the waveguide, that is the lithium niobate structure. And since here I have not defined any electrodes so far now, because I'm not concerned with the electro-optic effect right now, because I'm optimizing the dimensions of this particular waveguide. So electrode or potential is of no concern for us right now. So this particular term ES dot norm E will become 0 for now. So 0 externally. I showed this formula because I will be using it in further sessions, further parts of the same experiment. So I'll just here use NLI, which is 2.29. Now I will use, let's define SiO2, silica glass, refractive index of silica glass. So here I will use NSiO2, which I have received from Selmar equation. Okay, so this part of job is done. Electromagnetic wave equation. Let's check wave equation if it's correct or not. It's totally right. Here, this is the formula that is being defined with respect to refractive index, and if refractive index is achieved from the material, and that the material that we have defined in this section. It's giving me some warning. Okay, I have not defined the domain, that's why it was showing me the warning. Now it's not showing the warning, so that part is resolved. Initial values, let's see initial values. Okay, it's correct. Electric field initially has been put 0, so 0 initial condition is being taken. uh, Electrostatics, again this is not required for now, so we can disable it. We will, however, we will use it in future references. Now we will create mesh, physics control mesh. So um, free triangular and entire geometry. Right now I will be taking it for entire geometry, and we can use it for extra fine and build all. So here mesh is created, as you can see it's good to go. Now we will do the model analysis. Here, before doing the model analysis, you have to change the parameter, the value of lambda. Okay, so starting with this model analysis, let's see in starting, let's find it for 30 modes, and region around 1.4 is a good approximation. Compute. Okay, we are getting something. However, it's not it's not good, but okay, we are getting something. Let's check for others. As you can see, there are no modes inside the waveguide. However, it is like not the acceptable ones, not the one that we are looking for. Okay, so okay, fine. So there are two options we are having: this one and this one. Okay. Let me start again. Once again, I will do the model study, but now it's around 1.44 because in last study, as we saw, that we are getting a mode around 1.44. This time it will be only 2. So we have got these two modes. Now, now, as we can see that not entire power is being confined into it. Like what I'm saying is not entire mode is not being confined in. What could be the reason of it? So the probable reason that why the mode is not confining into the structure and like it's leaking outside width of the of the waveguide of lithium niobate. So what we will do is we will implement a parametric sweep. How this model analysis changes with respect to the different values of the width of the structure, right? Width of wave. So we will define width of the wave. So we can run it from 100 nanometers. We can place it 10 nanometers. We can place it 800 nanometers. Nanometers and Everything is good. What happens? Wait for the output. It will take a while. Here we will have to define the scattering boundary condition. Since I did not define it, so I wasn't getting the correct output. So you have to take care of this as well, that you properly define boundary conditions, because not defining the boundary conditions may give you the wrong outputs. Okay, now I'm getting better results. Now I can run the parametric sweep. Let's see what happens now. Again, we are not getting the desirable output. So let's uh, let's try it in this way. Modal analysis. Let's search for two modes. What we intend is we this this configuration. So job is here while studying the confinement factor. 447. Now I hope I get. Yes, I'm getting this configuration. Now I can again apply the parametric sweep and then we will compute. In this way, we will get the desired result, because see, selecting the right mode is a trick, and if you're not choosing the right mode, then you will not get the desirable output. And choosing the right mode is a very important point in doing this experiment. So I hope this time it will work. Okay, now we are getting the desired results. Let me delete this one so there is no ambiguity. So yeah, electric field. What I was now, as you can see in this electric field, as we increase the value of the width of the waveguide, like it's right now at 800, and effective mode index is 1.598 to something, then output, like most of the power is confined inside. Although there are some leaking modal distributions, but if you compare it with 400 nanometers or 130 or let's say 400 nanometer, which is the present value, you see a major part of value is confined inside. So for making a more like accurate analysis, we can use two different parameters on the basis of which we will decide that what is the rate and optimized value of the width of this structure of lithium niobate. The first parameter is confinement factor, and the second parameter is modal effective area. So for that, let me show you the equation of confinement factor. I don't think it's available on to the internet. Even though if it's not available, there is no issue. Yeah, here it is. So here at the core, divide by the total power of that is available and that is being given to the entire structure. So for that, what we will have to do is that we will creations, and we will have to find the power residing into the core, that is this particular region, divide by the power that is residing into the entire structure, this concerned structure. For that, we will define two integrations into the here we can define the integration. So let me show you how we can define the integration. Go here, you get the option of integration. This is for let's say I'm defining for waveguide region integration. I will use the domain. This is the domain in which I have to integrate, and it's integration out of 4. Okay, rest all is good, and the remaining one I have to do it for the entire body. So entire geometry and entire geometry. Okay. I will choose the domain accordingly and in the same manner. Now I have defined two different integrations. Now, okay, I'm good to go. Now here I can do the analysis of confinement factor and modal effective area using their respective equations. From here, you can use the integration that we have defined previously. And from non-local couplings, this is the Here it is in top one, so I will use in top one and uh, parameter that I have to use. So I have to find the power, and the power can be evaluated using the square of the electric field. So we can whole square confinement factor, and if I have to evaluate it using this, I will do is I will multiply it by 100 and this will give me confinement factor. Okay, and our next target is to find modal effective area. Let's see what is the equation for modal effective area. Let's see if I can find the equation or not, because it's really very hard to remember the equations of these values. Modal effective area. Okay, so here it is. I can use this equation. So it's the square of and this square of the entire integral divided by the power 4 of this integral. Okay, uh, this equation is correct or not. First we will implement and then we will check whether it's the right equation or not. So in top 1 and dot nor e का इंटीग्रल ही है square of this integral. Square, oh sorry, square of this integral. So, square of this integral divided by n dot 2. Let's see, n dot 2 power of 4. So fd dot nor power 4. See, this is yeah, it's we check it in top 1 integration of square and square of whole and integration of power 4, and is it the same thing? Yeah, it's the same thing. Okay, so entire configuration has been set. This is modal effective area, and this is confinement factor. We will evaluate. Okay, have to rerun it. Okay, so here I can see mode effective area and confinement factor. I think there's something wrong with this, because as you can see, it's displaying it 1 by meter square, which should not be the case. Let me check what is being wrong here. Okay. That part was wrong, so let's type it 100. Right value, okay. Now let's copy it and let's make a new Excel file. Uh, and mode effective area. Okay, so this is the confinement factor in terms of percentage with respect to the width of the waveguide. And let me create another graph of with mode effective area also, and then I will comment at how we will decide the optimized value. So yeah, as I've already said that probably the equation that we found on the internet was wrong, because uh, as the value increase, it must drop. So let's recheck that what mistake we are doing in it. And evaluate. So let's check now. Yeah, now it is correct. So as you can see, now we have two different graphs with respect to the width of the waveguide. On x-axis is the width of the waveguide, and on y-axis, left graph shows you the mode effective area, and right side shows you the confinement factor. Mode effective area, what it means is that how dense your model distribution is inside your waveguide. That is how densely it is situated inside the waveguide of the lithium niobate. So obviously बात है कि it is desirable to have highly dense optical distribution, optical field distribution, so that the modal effective area is desirable to have a very less value. So on introspection, we can see that from this particular value, from 600 nanometer, it is almost flat and it is significantly less, and it is tending to zero. And on the other hand, as you can see, the confinement factor refers to the ability of the waveguide to confine the modal distributions inside the substance, inside the waveguide of lithium niobate. So it's pretty obvious that we will need a higher value of confinement factor, so that more and more modal distributions could be confined inside the waveguide. So a higher value of confinement factor is desirable, and as on we can see on 600 nanometers, it is nearly about 27.127%, which is okay for the substances for electro-optic effect. So taking the intersection of both the results, we can conclude that at 600 nanometers, uh, your design, your the waveguide is optimized and giving you satisfactory results. So now I can make it 600 nanometers here. I can make it 600 nanometers. I can remove parametric sweeps. Let's just disable it and run it for one last time and see whether we are getting good results or not. Yeah, now you can see a major portion of power is confined inside it. A very dense model distribution is into this particular area of the waveguide, which we require for the wave propagation. So with this, the first step of optimization of the width of the waveguide is completed. Thank you very much for watching this, and in the next part of of the same experiment, the agenda of ours will be to optimize the distance between the electrodes and this particular waveguide. Thank you.